Hello again, everyone. Welcome back for week 2, which is chapter 2 of our statistics course. Today we're going to look at organizing data. So we talked a little bit last week about types of data. We have the qualitative or categorical data where the answer to our question being asked puts you in a category like favorite color or any yes or no question or what degree you're enrolled in, things like that where it's a categorical answer. And we had quantitative data, where it's numerical data. The answer to the question is a number. And that broke down even further into discrete, where it was counted, like how many classes are you taking? How many children do you have? Or continuous, where it was measured. How tall are you? How long does it take you to complete a given task? Those are all things that were measured, so they were continuous data. Today we're going to look at organizing some of that. And so we're going to start out in chapter 2 here. We have organizing in tables, graphs, and then some discussion of good graphs and deceiving graphs. We're going to start off today looking at just what is the purpose of summarizing data. So when we look at large data sets, it is often very difficult to get a good feel for that data without organizing it somewhat. For example, this data set here, if we are looking to choose new school colors and we want to choose a dominant color, and we give people a choice between red, blue, and green, and here we have a list of their responses. Well, looking at that, it is really difficult to get an idea of what the most common response is. Human psychology tells us the human brain can really only view about 13 items at once before things blur out around the edges. So when we're looking at this, we're only seeing part of it. If we're looking right here, we might be seeing, well, red. There's a lot of reds there. Red might be their dominant color. If we were looking closer into this area, we might see blue is the most common response. If we're looking down here, we might see green is the most common response. So we need to organize that data somehow so we can get a better feel for really what response is the most common there. And so one of the tools we use for that is a frequency distribution or a frequency table. So when we deal with a frequency distribution, first thing we have to do is figure out what groups we're organizing it into. Now this talks about classes and then their frequency. There's really 3 different types of frequency table. We can have qualitative data, and that gives us a frequency table where we just have a list of all those different categories that could be responded and their frequency. We'll look at the color for the new school color in just a little bit, and then the frequency of that would be calculated and put in the other column. There is what we call limited response, discrete. So limited response discrete data is where it is discrete, it is counted, so it's just going to be set counting numbers, 0, 1, 2, 3, 4, 5, or maybe we don't even include 0 in there. So we can list them all out. Limited response means it only goes up so high so that we can list out all of those different possibilities and give a frequency for each of them individually. We'll see an example of that as well. And then there's large response discrete. And that gets lumped in with our continuous data. If we're looking at maybe how many speeding tickets have you had in your life? Well, some people may have had dozens of tickets or parking tickets maybe. Speeding tickets, you probably wouldn't have a license anymore. But parking tickets, I know people that have had 30 or 40 parking tickets. I know others that have had 0. We don't want to list out 0, 1, 2, 3, 4, 5, all the way up through 40. That's too many different categories. So we would group them. We're looking at continuous data, like how tall are you? Well, we could go down to the 10th of an inch. We don't want to list out all those individual heights. So again, we group them. So when we're dealing with large response, discrete, or continuous data, we have to group the data. So this is going to go on talking about that grouped data. We're going to jump off from the PowerPoint for just a second, and we're going to look at some of the examples of categorical data or qualitative data here. And this is that example I talked about of we're going to choose a new school color. And we have three choices, red, blue, or green. And we want to know what people chose. So now a finished frequency table would just have the color and the frequency. So we'd have red, blue, green, and we have the frequency listed. But we still have to construct it somehow. So to construct it, often it's easier to use a working table. And instead of just listing the frequency, I'm going to do a tally for now. And all that is just this. So I've got red, blue, red, red, blue, red, blue, red, red, blue, green, red, red, blue, red, green, red, red, blue, red, green, blue, blue, green, red, green, blue, blue, green, red, blue, 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 green, blue, 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 green, blue, red, blue, green, green, blue, red, blue, green, green, blue, green, red, green, green, blue, green, red, green, green, blue. Halfway there. Red, red, green, red, 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 green, red, red, blue, red, green, blue, 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 red, green, blue, blue, red, blue, green, blue, blue, red, blue, green, blue, blue, green, red, blue, blue, green, green, red, blue, blue, green, green, red, green, 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 blue, green. So there's our tallies. That gives us our frequencies. Now we could have gone through and just tried to count the R's and then tried to count the B's and whatever, but we often miss one or miss some of them as we go through there that way. Here we have our tallies. Let's add them up. On the top we got 5, 10, 15, 18 for red. For blue, we have 5, 10, 15, 20, 22 for blue. And for green, 5, 10, 15, 20 for green. Now, looking at that raw data, just those responses, the R's, B's, and G's, we never would have guessed that it was going to be that close in our final response. So there is a frequency table for categorical or qualitative data. You'll notice I've been very careful not to use the three colors, red, blue, or green, in my table because I don't want to influence you by putting color out there. Even with the numbers there, we're visual people as humans. Seeing a color, our mind would latch on to that, tend to latch on to that, and might skew our perception of that data. Now, one thing I'd like to add to this is I'd like to add another column listing relative frequency. And we'll come back to calculating relative frequency after we go through it in the PowerPoint. Now, I said something about limited response, discrete. If I ask you how many classes you're currently taking, let's say if you answer 0, you're not a current student, so we don't include you. So 1 is the smallest number you can have. Let's say nobody responds more than 6 classes at a time. And so we'd have their number of classes and their frequencies, the number of people that are taking that many classes. Here, because it's limited response, there's a limited number of numbers that can be responded here because you can only take so many classes at once. We are able to actually list out all of those possible responses in the table here. So each of these frequencies is for an individual number. That is for 24 people that are taking 2 classes. This is 61 people that are taking 4 classes. So we've broken it down by each individual number. But in many cases, the number of responses is too large to list out all the possibilities. And that's where we come back to our PowerPoint here. We have to group the data. And so when we group our data, we need to create classes. And each class is going to have some features. One is the lower class limit. That is the smallest number that belongs into each class. The upper class limit is the largest number that would go into each class. And the class boundaries are actually between the upper class limit of one class and the lower class limit of the next class up. It separates out the classes. Class midpoint, that is just found by averaging together the lower and upper class limit for a class. So it's what's right in the middle of that class. The class width is then how wide each class is, taking the lower class limit of one class, subtracting the lower class limit of the class below it. So if we construct this grouped frequency distribution, we need to first come up with how many classes we're going to have. Usually we'll decide, this book recommends somewhere between 5 and 20. I mean, you can usually get down to, I wouldn't go less than 4. 20 is getting to be a lot. I'd say between 4 and 12 would be ideal. So first we're going to calculate an approximate class width. So to do this, we need to find the range of the data. That's just taking the largest value of the data minus the smallest value of the data. We haven't used this term yet for this class, but I think most of us have heard the term range enough that we don't have to wait till we officially define it in here. And then divide by how many classes we want it. So we come up with a convenient number. Usually we'd round that up so we have more classes than we need. And then we set up from there, then we determine what our class widths are. So then once we have determined how many classes we have and what our class width is going to be, then we choose a value. Where do we need to start our first class? This has to be at or below the smallest data value. Sometimes we just pick that smallest data value and go from there. Otherwise, if there's a convenient division, like if we're looking for letter grades, a lot of times we just use the letter grade ranges for those values. We need to pick the lower class limit for the first data set. And then from there, we use the class width. We add that on to determine the lower class limit for the next data set, which is step 4. The next class limit we just find by adding that class width to that lower class limit. Once you have all the lower class limits in, then we can go and find the upper class limits. It has to just stay below. The upper class limit has to be smaller than the lower class limit of the next class up. When we deal with that, we have to look at the precision of our data. If our data is rounded just to the nearest 1, well, that upper class limit is just going to be 1 less than the lower class limit of the next class. If we're going to the nearest 10th, however, we have to make sure that we're only 1/10 below that lower class limit of the next class, so that there isn't gaps between classes. Then we take each individual data value and we make tally marks. Like we did there for the colors, we did the tally marks so that we could count them up. And then we came back, here we did the tally marks here to count them. But then we came back and actually made the official frequency table. It doesn't have tally marks in the official frequency table, but it helped us. Those tallies helped us to add up the frequencies for each of those possible responses. So here's an example. We're looking at the commute times of people in Los Angeles. These are all rounded to the nearest minute, so no decimals. The range of data here, let's just take a peek. Our smallest value, we've got a 5 in there. That looks to be the smallest one is the 5. So 5 would be our smallest value here. As we have for large values here. Okay. I'm looking at the data table. I see that 90 appears to be our largest data value. I'm not seeing anything bigger than that. So that's our range, 5 to 90. 90 minus 5 would give us 85 as our range of our data. We decided here that we want 1, 2, 3, 4, 5, 6, 7 classes. So we do 85 divided by 7 gives us 12 point. 1, 4, 2, 8, 5, 7. So rounded up, probably 13 or 14. They decided to go with 14 here just to be sure, because we're going to start at 0 because it's a convenient point to start at 0 rather than 5. And we make our classes. So we decided to go with a class width actually of 15 just to make it a little more even numbers. So you can see we did the 0, 15, 30, 45, 60, 75, 90 as our lower class limits using that class width of 15. Now I might have been tempted to use 14 or even 13 here, just so that the upper class, you can see the largest value of 90 is actually the lower class limit of that upper class. Most of that upper range is beyond what our data gives us. I don't like to overshoot quite that far, but it is nice and convenient to use 15 as the class width. It's way easier to count up by 15s than it is by 14s or 13s. And then, of course, we had to create the upper class limit for each class. And we did that by looking at the data. This data is rounded to the nearest minute, so we only have to be within the nearest 1. So I take, for this upper class limit here for the first class, I look at the lower class limit of the next one is 15, and I just subtract 1 to get 14. For this one here, I look at the next lower class limit, which is 30. I subtract 1 to get 29. This is because we're subtracting 1 because the data was just to the nearest 1 unit. If the data went to the nearest tenth of a minute, so if it was 18.3 minutes instead of just 18 minutes, then our table has to be done to the tenth of a minute. So what that would have been is we would have taken the 15 here, which is the lower limit of the second class, we would have subtracted a tenth or 0.1, so that this would have had to have been 14.9 here. And then this would have had to have been 29.9, and so on, so that there aren't gaps in between classes. So we have to be very careful when we set up our classes here. One, that the classes have a wide enough range that they contain every data point. Two, the classes are all exactly the same size. These all had a class, so not a class width, but width from one to the other is a 14. And there's no gaps in between classes. There's no way that data points can fall in between classes. So we've got all three of those requirements here. So we selected that 7 as our number of desired classes. We did the division. We saw that we rounded from 12. We just rounded up to 15 because it was a much more convenient value. Now we selected 0 as our first class limit just because even though 5 was the smallest number, 0 was just a nice, easy spot to start counting up from. And then we went up by 15. So we had 0, 15, 30, 45, 60, 75, and 90 were our lower class limits. We can see that was where we started in our table. Then to get our upper class limits, we subtract. Our data, again, only goes to the nearest 1. So we could subtract 1 from the following lower class limit to get the upper class limit. Like we said, 15 minus 1 gave us 14 here. 30 minus 1 gave us 29 up here. 45 minus 1 gave us 44 there. Now we can fill those in. Again, that we subtracted 1 because the data was rounded to the nearest 1 minute. If it was rounded to the nearest tenth of a minute, we'd be subtracting 1/10 or 0.1. If it was the nearest hundredth of a minute, we'd be subtracting 0.01. So we have to pay attention to what our data is rounded to figure out how we find that upper class limit to make sure there's no gaps between classes. So then here are our actual classes, and then we counted the frequency for each. So the next step is something called a relative frequency distribution. The relative frequency distribution tells us what portion of the data is in each class or each group. We do this, first thing we have to do is find the total. That is the sum of all the frequencies, the total frequency. And we take each individual frequency and we divide by that total. Now, if we left it as this decimal, which would be a rate technically, that would be called the relative frequency. We could convert that decimal into a percent by moving the decimal over 2 spots or multiplying by 100. That would be a percent frequency. They really tell us the same thing. It's just a little bit different way of expressing the exact same thing. So we can get a relative frequency distribution by calculating either those percents or that decimal proportion and leaving it that way. The biggest thing here is those sums of those relative frequencies. If we do it as percents, they should add up to be 100 or really close to 100 because it should add up to the total. Now you might say, well, why don't they always round up to exactly 100? Well, because sometimes if we have a really awkward frequency, the total frequency might be 42. When you divide by 42, you're going to get some really strange decimals. You're going to want to round them at some point, and that round off error can cause us to be maybe 99% or 101%. So it might not be perfect as we add up all those percents. It might not perfectly come out to 100, but it should be very close. So here, we've changed this to relative frequencies. So let's look at how we got those relative frequencies. Back up to this table here. We found a total here for these frequencies. So 6 plus 18 is 24, plus 14 is 38, plus 5 is 43, plus another 5 is 48, plus another 1 is 49, and another 1 is 50. So we got a 50 is our total frequency here. So then our percent or our relative frequency, we'll do the relative frequency here. Is this frequency divided by that total of 50. So 6 divided by 50 gives us 0.12. 18 divided by 50 gives us 0.36. 14 divided by 50 is 0.28. 10 divided by 50 is 0.1. 5 divided by 50 is 0.1. Another 5 divided by 50 is also 0.1. 1 divided by 50 is 0.02. And of course, another 1 divided by 50 is also 0.02. Here, those add up to exactly 1.00. So if we leave them as relative frequencies instead of turning them into percents, that's what they should add up to, is exactly 1. Here, our total was 50, so when we divided them out, we got nice even results, so we didn't have round-off errors. Again, other totals, we might have to round them off, and we might be slightly off from the exactly 1. If we change those to percents like we did here, all we did was move the decimal over. The 0.12 became 12%. 0.36 became 36%. As you can see, this total should now add up to 100%, or again, something really close to it. So we're going to come back to combining relative frequency distributions. Let's look at this situation here. So we have a total here. If I add these up, what is that? 60 responses. So as I said, there might not always be nice and easy. Dividing by 60 could give us some weird decimals. Well, 18 divided by 60 is 0.3. That one's just fine, so 0.30. However, 22 divided by 60, that ends up being 0.366666. So it would be 0.3667. We'll just go to 4 decimal places. 20 divided by 60 is 0.3333. Again, we'll round to 4 decimal places. Well, here, because one rounded up and one rounded down, this does still add up to exactly 1.0000. Works out just fine, but it could, again, you can see how those round-offs could affect that and cause it to be slightly away. And of course, you could make these percents by just moving the decimal over 2 spots or multiplying each of them by 100 to make them percents. Down here, you can do the same thing. I'm going to save this one, though, for a cumulative frequency table in just a little bit. So comparisons. One of the things that these relative frequency tables are good for is they allow us to compare two data sets. Even if we have a different total frequency, we can compare the percents. So here, we want to compare the commute times between New York and Boise. We might not have the same number of commuters in each area. We'd expect to have a lot more in New York, but we can compare the percents. A large percent of the commuters in Boise commute for less than 14 minutes, or only very few in New York. Whereas in New York, it looks like the largest number commute for 30 to 44 minutes. In Boise, it looks like the largest number is only 15 to 29 minutes. So we can compare between two different groups. Even though they have very different frequencies, total frequencies, the percents are still comparable. So here we're looking at, because of the different sizes of these two cities, we have expect different commute times to be very different. We can't compare the raw frequencies because there's a lot more people in New York, but we can compare those relative frequencies or percents. It appears that Boise, because of this table, has shorter commutes than New York does. The next thing we want to look at is something called a cumulative frequency. This is actually the same data table as we had up here, actually all the way up here even. But we have converted it into, it's the same set of data, but we have now converted it into a cumulative frequency. What the cumulative frequency is notice here, instead of doing 0 to 15, it just says less than 15. Well, it's still 6 because less than 15 is just 0 to 15. I should say 0 to 14, I should say. Because 15 isn't less than 15, so that only goes up to 14. This was the 15 to 29, or less than 30. Notice if we went back to our original table, we had 6 that were 0 to 14, 18 that were 15 to 29. That would add up to a total of 24, which is exactly what our cumulative frequency is showing us. There's 24 that are less than 30. So what we're actually doing is we're adding up the frequencies as we go. So less than 45, that includes the 0 to 14, the 15 to 29, and the 30 to 44 classes from our original frequency table. When we get to the bottom one here, this bottom frequency better equal our total frequency. We only had a total of 50 commuters here. That is 50 is that last cumulative frequency. So let's come back here to this example quick. So if I want to find the cumulative frequency here, I would change the table. This would be less than or equal to 1. That cumulative frequency is just the 18. It's just the 1. Next would be less than or equal to 2. Well, that's the 24 for the 2 plus the 18. There's 42. Less than or equal to 3. That's the 54 plus the previous 42. So that's 96. Less than or equal to 4. So that's saying from the 4 or less, we add the 61 onto that. Here's 157. Less than or equal to 5. We add the 27 onto that, giving us, what is that, 184. And then finally, less than or equal to 6. We add the final 16. We get 200. Now, if we had added these up, we would have had a total frequency of 200 there. So that last cumulative frequency gives us 200. So next we want to talk about using distributions to understand distributions of data. So data can be distributed in different shapes. We're often interested, the shape that we're often interested in is that bell curve, which is what we call normally distributed data, or a normal distribution. In this case, the frequencies start low. If we're looking at our frequency table, they get larger and then they get smaller again. So basically, If we're looking in our table, these first few classes have low frequencies, these have larger frequencies, and then the bottom classes have smaller frequencies again. That is oversimplifying the normal distribution a bit, but that is kind of the first thing you look for at a glance. So here would be kind of an example of a normally distributed set of data. The smaller numbers, the lower classes have small frequencies. They get a little bit bigger as we get to the middle. The biggest ones are in the middle. Then as we get into the higher values, those frequencies decrease again. Now they make it symmetrical because technically a normal distribution would be symmetrical, but in application it doesn't have to be perfect as long as they're close. They made this one perfect, so it's way, really close to a normal distribution. Gaps in the data would tell us that it's not a normal distribution. Also, gaps in the data tell us we might actually be drawing data from two different data sets or two different populations or subgroups of the population and trying to combine them together. So if we see this, we need to stop and figure out why are there gaps in the data, or if there's two humps in the data, two spots where the frequency gets large but they're not right together. We might be drawing from different commuters. So here, let's look at, this table is looking at the weight of penny in grams. So pennies, in 1982 is the exact date. I believe they said 1983 in the textbook. That is wrong. The U.S. Mint switched from making mostly copper pennies with a little bit of zinc in them to making zinc pennies that just have a copper coating on the outside. If you were to cut a new penny in half, it's actually silver. It's zinc on the inside. It's just a very thin copper coating on the outside of it. Whereas before 1982, they were solid copper. Well, you would imagine those copper pennies are heavier than the zinc ones. So if we take down the weight in grams, technically it's mass if we're measuring in grams, of randomly selected copper pennies, or just randomly selected pennies, we see we have some of them that are really light and some of them that are really heavy, and then we have this gap in the middle where there aren't any. That's because there's two different kinds of pennies here. One is the solid copper pennies, and the other is the zinc-filled pennies. They're not from the same population. That's two different populations. We're trying to combine it into one data set, and we can't do that because that data does not go together. If you want to examine the frequencies, when we look at the frequencies, and we see that gap, that tells us there's something to look for. Again, they screwed up here. They said 1983. It was technically 1982 that the Mint switched. Halfway through 1982, actually. So some 1982 pennies will be mostly copper, and some of them will be mostly zinc with the thin copper layer. Because of that, drastic differences in their weights. So that explains the gap that we had in that table, the fact that there were no values in these middle groups or middle classes of this table. It's not always going to be that simple, but seeing that gap in the data alerts us that we need to go look for a cause. Now, the next thing I want to do is, before we move on to section 2.2, I want to look at using technology here a little bit, Excel. So here's a set of data that I made up, and this is talking about number of parking violations that students have had on campus. So we randomly selected 40 students and looked at their parking violations. These are bicycle parking violations, by the way. I already went through and I checked. Our data ranges from 8 up to 30. So 8 is our smallest value, 30 is the largest, 32 is the largest. So we would do 32 minus 8 gives us a range of 24. Now, I just want to break this down into 5 classes. So 24 divided by 5 gives us 4.8. So I can get away with a class width of 5, going from one lower class limit to the next. I'm just going to start out at 8, which is my smallest data value, and I'm going to add 5. So 8 plus 5 gave us the 13. 13 plus another 5 gave us 18. And we keep adding 5. Now these are counting values. You can only get one. You can't get a half a ticket or a tenth of a ticket. So it counts up by 1. So to get this upper class limit, I take this lower class limit and subtract 1. So 13 minus 1 is 12. I look at this lower class limit. 18 minus 1 gives me 17 for this upper class limit. And I fill in those upper class limits. Now this last one, there isn't a lower class here to subtract from, but I just look. These go up by 5 each time. I go up by 5 again to get the last one. Now Excel will fill in these frequencies for me. It will find those frequencies for me, I should say. But it doesn't organize them into a proper frequency table very well. And so the function we use is we go to the data menu in Excel, right? There's the data menu. And in the data menu, we have the data, oops, get my recording bar out of the way here. In the data menu, we have an Analyze tab over here. Now, some of you, your tab might be empty there. I have the Data Analysis Tool Pack and the Solver in here. If you don't have those, you're going to need to go to your add-ins and add in the Data Analysis Tool Pack. There are actually 2 add-ins for Data Analysis Tool Pack, and there's one for the Solver. Add them in, and they'll appear here. So we select the Data Analysis, and we have several options here. We scroll down to Histogram. Now, I know we're creating a frequency table, but Excel creates a frequency table as part of creating a histogram. Input range, this is where our data is. So I click in that, and then I just come over here and I click and drag to highlight my data set. So that's telling Excel that my data is in there. Notice it does A1 to A40, telling the Excel that the data is in those cells. The bin range. Now notice I put these in separate places. I could just enter 12, 17, 22, 27, and 32, but it's easier just to click and drag to highlight those. It's asking for the upper class limit for each grouping. Labels, I'm going to leave that off there because if I clicked labels, it would say that the top number in the bin range was a label. It's not. I just use numbers. Output range, we need to tell Excel where we want this table. So I'm going to click output range, and I'm going to just click here, and I'm going to click an empty cell here. When I click OK, it's going to give me that frequency table. Now notice it just gives the upper class limit for the bin. We would want to go back through and put in that lower class limit, 8 to 12, not just 12. And this would be 13 to 17, and so on. So we would want to redo that table to make it fit. Now we notice there's other things in there. I'm going to clear this all out quick. And I'm going to go back to that data analysis again. So when I open up the histogram data analysis thing here, I still have my input range and my bin range, and I'm going to put my output in the same spot. But I'm going to click now Pareto or sorted histogram. In the next section, we'll look at histograms. Collecting that would cause us to create a histogram. We're going to leave that off for now, and we'll talk about that in the next section. Cumulative percent. So not only can we have a percent or relative frequency and a cumulative frequency, we can combine them and have a cumulative percent frequency. We'll go ahead and do that. So let's click that, and I'll show you what happens. So you can see we get the percents in a cumulative fashion. So instead of just the percents or the relative frequency for each class, they're added up cumulatively. Notice the bottom one's 100%. And there are some other options there we can play around with. We're not ready to make charts yet, so we're going to leave it at that for now. So the second section of Chapter 2 now brings us into displaying that data more graphically. In Section 1, we organized it into data tables or frequency tables. And now let's look at displaying it more visually. So we're talking about histograms as our main type of graph here. A histogram is for numerical or quantitative data. We did look at categorical data like this, and the equivalent for categorical data or qualitative data is a bar graph. And we've all seen a bar graph before. So a bar graph takes our categories here. We've got the red, blue, and green are our three categories for this data set, and puts them along an axis. Generally, statistically, we put them along a lower horizontal axis. Then we have numbering going up, the number scale going up the side, the left side. So let's do 5, 10, 15, 20, 25. And we draw bars. So red goes up to 18, so we'd have a bar that goes up to 18. Blue goes up to 22. Green goes up to 20. Now I'm trying to be careful about a couple of things. One is, I didn't do a great job of it, but I'm trying to make sure these bars are all the same width. Because making one bar a little wider than the other, you can see here the red got a little wider than the green. Even though it's shorter, it almost looks bigger. Our mind wants to make it bigger because our mind sees areas rather than just seeing the height. Similar things happen with the spacing. If I made them closer together, I tried to keep the spacing between them the same so that we didn't have any of that effect as well. There's a lot of psychology in the accurate presentation of statistics. It's real easy to present statistics in such a way that you accurately present the numbers, but you trick somebody's mind into seeing them differently than what they actually are. We'll look at that a little bit more in section 3 when we look at misleading graphs as well. For our numerical data, this could be done as a bar graph or a histogram, since it's numerical data. The biggest difference would be, we have those categories across the bottom. It's just going to be 1, 2, 3, 4, 5, 6 now. These are numbers rather than word categories or qualitative categories. We still have a scale going up the side. This one's going to be a little bit more spaced out. So 10, 20, 30, 40, 50, and 60. And when we put our bars up, we've got 18 for 1, 24 for 2, 3 would be 54. I'm not going to keep going here just for the sake of time, but one thing you might notice is there's no space between the bars here, where in the bar graph there was space between them. And this is on purpose, and there is a meaning to it. With categorical data like red, blue, and green, there is no logical connection from one category to the next. In fact, there's no logical order. I could put those in any order and it would make just as much sense. But with numerical data, 1, 2, 3, 4, 5, 6 needs to go in that order because that's their numerical order. And there is a logical link from 1 to 2 and 2 to 3. So we put the bars tight together to give that psychological effect again of a connection from one to another, a flow from one value to the next. So as we come back here now to explore histograms with grouped data, key concept here is the histogram is going to be a better tool for visualizing than a table, mostly because you don't have to read the numbers. You can just look and compare sizes of the visual pieces of the graph. So all a histogram is, it's similar to that bar graph, only the bars are tight together and our categories are numbers rather than qualitative categories. So important uses. 1, we can show the distribution of the data. 2, we can locate the center of the data. We can see the spread, how wide is the graph, how spread out is the graph. And then we can identify outliers. Outliers are data points that don't fit in with other data points. So if we have a gap in the data, in the last section we saw that a gap in the data could indicate that we were gathering data from 2 different populations without knowing it and trying to put the data together. If it's just one data point that's out away from the rest of the data with a gap in between, it might just be that we have one outlier, one unusual value that doesn't fit in with the others. So a variation of our frequency histogram, just like we have the regular frequency table and the relative frequency table, we have a frequency histogram and a relative frequency histogram. So here is our standard frequency histogram here, where you can see up the side we're numbered 5, 10, 15, 20. And so the height of the bar indicates the actual frequency. So the 22 here is the center of that class. That's at 18. There are 18 people that had times in there. Now to read these classes down here, this cutoff here is the cutoff between 7 and 22. We average those together, that would be 14.5. Remember we had said that this was 0 to 14 is that first class, 15 to 29 is the next class. That's what the 14.5 is between the 14 and the 15. That's our cutoff. So these are still those ranges of values. We just put in the center of the class midpoint, to make it easier to label them. Some textbooks ask us to use the class midpoint like this. Other textbooks ask us to use the range like this. I prefer to use the range, but this textbook uses that class midpoint. And then over here, we have the relative frequency distribution. Instead of frequencies, raw numbers like we had there, here we have percents. Notice the bars are still the exact same height, same width, same shape. It's just the label, the axis on the left side is labeled different. Instead of this lining up with 18, it lines up with like 37%. So histograms, as we said, can display center, variation, distribution, and outliers. And we can also look at timing of certain things. We'll take a peek at that as we go through here. This textbook uses the CV dot. Really not necessary to memorize that, as long as you understand what the graph is telling you. So common shapes. So here we have, this is just that basic bell shape. You'll notice it's pretty much symmetrical. Same shape on either side. That is our normally distributed set of data, or bell shape. This here is uniformly distributed because all the bars are really close to the same height. There's not much difference from one to another. So uniformly distributed says the data is spread out equally across the whole range. So in other words, each class or each range within that range has about the same frequency. These bottom two are both variations of the normal distribution, or variations off of the normal distribution. They're distributions that are not quite normal because they have a little bit, they're stretched out on one side. So this one here you can see is that bell curve that is stretched out on the right side. That is said to be skewed. So then the brown one here, basically, again, close to bell shaped, but it's stretched out on the left side, so that is considered skewed left. We'll talk more about skewness as we look at other effects of data. So approximately normal doesn't mean perfectly normal. You can see here there's the bell curve with those bars. Those bars don't fit perfectly underneath it, but you can see it's close. And so when we're talking about normally distributed, that's what we're talking about. Some more advanced courses will talk about changing the width of the classes so that the bars are closer or narrower or wider to make it come even closer to being a perfect fit to that bell curve. So skewness, as we said, is anything that makes it not perfectly symmetrical. It's still close to that bell curve. It has that hump, but it's just stretched out to one side or another. This was skewed to the right because it's stretched out on that right tail. This is skewed to the left. Oops, I can get switched. There we go. Because it's stretched out on that left tail. It's stretched out more than the right tail. Next, I want to talk about assessing the normality. And one of the tools we use for that is normal quantile plots. So we look at the graph here and we can see it's about a bell curve, but it's not perfect. How close is it to being normally distributed? So using the normal quantile plot, we can get a better assessment of that. So the normal quantile plot, we match up our points, the data, to points on a plot, and we see how close it falls to being on a straight line. So let me do an example of that here. Actually, I want this set of data over here. So here I have a set of data. It's only 10 data points. I'm using a very small set just to make it easy. I'll make this a little bit larger. And I'm going to move these data points over. I'm going to copy and paste them just so we can use them. And the first thing I need to do, that's not what I want. Let's make sure I get the whole data set. There we go. First thing I need to do is make sure I put them in order. So I'm just going to go to data and I'm going to sort them to get them smallest to largest. Now they're put in order. I am going to now copy and paste those. So I got room to do a little work with them. Here I am going to label this as I. I is just going to be 1, 2, 3 on up. To just put a number in each of them. The smallest number is I1. Largest number is going to be I10. N equals 10 because there's 10 numbers in this list. This, of course, is our X value. So I'm just going to call that X with a little I. So that is the X value, and the I is just X1, X2, X3 in order from smallest to largest. Now I'm going to define an A value. So it's an AI. This value is equal to 2 times the I value, so 2 times this 1, minus 1, divided by 2 times the N value, so 2 times 10 in this case. That's what went wrong. Something didn't quite work there, so it should be 10, not 100. There we go. So we get 0.05. And I'm going to do that for each of these. I'm just going to copy this down so it does it for all of them. And you can see what we get here is we get a list of numbers that are evenly spaced from 0 to 1. And that's what we want for the normal quantile plot. And now we need to calculate a z-score here. Actually, not a z-score, a z-score for that probability. Now, we don't know about normal probabilities yet, so you're going to have to just take my word on this one. This is going to be a normal inverse for this value. So this value, this AI value, becomes a probability. And when we do the inverse normal, we get z-scores that'll range between negative infinity and positive infinity, usually between negative 3 and positive 3. So here we get negative 1.645 up to a positive 1.645. So what we want to graph now is the X value. So I'm just going to copy this and move it over. And this z-score that we got. So I'm going to copy that. Now I got to paste this so I get just the values. And I'm going to graph those on a scatter plot. So I do insert and just select a simple scatter plot. Now this scatter plot, the closer these points are to being on a perfect line, the closer this data is to being perfectly normally distributed. Now I can draw a line through here. I can get to the line tool, there we go. Relatively close to those points, not too far off. So this is pretty close to being normally distributed. There is not really well, you might see a set pattern here. You might look at this and say, well, it looks like it's kind of almost like a sine wave around there. But it's not evenly spaced. It curves faster here than it does down here. So I'm willing to say that this is not a set pattern, a predictable pattern. That those points are close to the line, but not varying away from it in a systematic way. So this set of data is actually relatively close to being normally distributed. So coming back here to the PowerPoint, looking at those are the 2 qualifications we must have. The points must be close to that line, and they cannot show any systematic pattern as how they deviate away from the line. So for this one here, those points are not really close to the line, but they're not terribly far away. So this, we would say that this is reasonably close to being normally distributed. There's definitely no systematic pattern to the points. This one here, well, the points go way down below, comes up like that. They are nowhere near the line at the beginning there, and definitely a systematic pattern. That actually looks more like an exponential curve than a straight line. So I would say those are not, that data set is definitely not normally distributed. This last one is where a lot of people mess up. These points are close to the line, but it's a very predictable pattern. You can see it waves above the line there, back down, almost like a sine wave pattern. And so even though those points are fairly close to the line, I would say that this data is not normally distributed for this data set. So that is histograms and assessing normality a little bit. And we'll come back to the next recording. We'll do sections 2, 3, and 2, 4 from chapter 2.